Hello, I'm sharing my screen. We will wait for some more time. Are you able to see my slides? Excuse me.
Yes, ma'am.
Okay, one second. We will start in 1 2 minutes. Like someone will be joining again, so it will be a disturbance. So we will wait for 1 2 minutes and we will start. We can start now. Good evening, all. Welcome back to NPTEL PMRF tutorials on Introductory Organic Chemistry 2 by Professor Harina Chakrapani and Professor Neeraja Deshaputri. Myself, Anisha Suresh, PMRF TA for this course from IIT Bombay. Excuse me. Sorry for the disturbance. So we have been conducting tutorials from last 4 weeks where we have discussed previous year assignment questions for this course for the previous 4 weeks. Today I'm going to discuss week 5 assignment questions of previous year for this course Introductory Organic Chemistry 2 based on enols and enolates. If you have missed my class for the last 4 weeks, you can go to YouTube link and you can see the videos there. Now, can we go to question number 1 for this week assignment? Coming to question number 1. In the given reactions, identify the correct combination of their major products P and Q. Here they have given a ketone and excuse me. So in this question, they have given a unsymmetrical ketone and they have treated it with LDA in THF at minus 78 degrees Celsius. It will generate one enolate and upon treating with benzaldehyde, it will undergo aldol reaction and it will give an aldol product P. And similarly, here they have a cyclopentanone and they have treated it with LDA in THF at minus 78 degrees Celsius. It will generate one enolate and upon treating with benzaldehyde, it will give a product Q. So they have asked to identify the major products P and Q, and these are the options given. Here it is a syn-aldol product. P is given as a syn-aldol product. Q is just given as one aldol product. Then in this option B, P is given as syn-aldol and Q as well as syn-aldol product. Here in option C, P is given as syn-aldol product and Q as anti-aldol product. Excuse me. And in option B, P is given as an anti-aldol product and Q is given also as anti-aldol product. So before going to the mechanism of these reactions, we want to know a rule for diastereoselectivity. So for diastereoselectivity in aldol reactions, generally it is not always true, but generally in aldol reactions, a cis-enolate upon treating with an aldehyde will give a syn-aldol product and a trans-enolate upon treating with an aldehyde it will give an anti-aldol product. This is a general rule and it will be applicable in the reactions that is given for us in the question. Keep in mind, a cis-enolate will give a syn-aldol product and a trans-enolate will give an anti-aldol product. So this should be kept in mind while we are dealing with our question. So coming to the mechanism, here we have a tertiary butyl and ethyl substituted ketone and a base is given LDA. Sorry, like here we have a tertiary butyl ethyl substituted ketone and upon treating with LDA, it will generate an enolate. Excuse me. Can I continue? Okay. So upon treating with LDA, here there is no alpha hydrogen. For in formation of enolate, the presence of alpha hydrogen is mandatory. So here there is no alpha hydrogen. So enolate will form in this side. Here there are two alpha hydrogen, one and two. So an enolate will be forming like this. This is a cis enolate because the groups having higher priority are coming on the same side. Here O lithium and here methyl group, they are the groups having higher priority on either of these carbons. So they are coming on the same side. So this is called a cis enolate. And here only cis enolate will be formed so as to make this tertiary butyl, which is a bulky group, and this methyl group on opposite sides. So here cis enolate will be forming in this case, and once cis enolate is formed, it will react with this benzaldehyde and we will get this syn aldol product. We have seen that in diastereoselectivity, a cis enolate will give a syn aldol product. Excuse me. So a cis enolate is formed here and it will give a syn aldol product. If we choose the group X, here the group X is the larger group tertiary butyl. So if a group X that is next to the carbonyl group is large, it will generate only cis enolate, and that cis enolate upon treating with aldehydes, it will result in formation of syn aldol product. So the cis enolate will lead to formation of syn aldol product. This is clear for everyone? How cis enolate is forming here and how it is leading to formation of syn aldol product. According to the rule of diastereoselectivity, generally a cis enolate will give a syn aldol product and a trans enolate will always lead to formation of a trans aldol product. That is general. There can be some exceptions. And coming to our second question, here we have cyclopentanone, and cyclopentanone upon treating with LDA, it will result in the formation of this enolate. This is a trans enolate because the groups having higher priority are coming opposite to each other. Here this O lithium and this group are coming opposite to each other. So they are called a trans enolate. Here the trans enolate upon treating with this benzaldehyde, it will result in the formation of an anti-aldol product. Here, trans enolates are formed because they are derived from cyclic ketones, and here they will form exclusively trans enolate and no cis enolate will be formed. So, this trans enolate will lead to formation of anti-aldol product. Is this clear for everyone? How syn aldol product and how anti-aldol product are formed in both these cases? Is this clear?
Once again, repeat, ma'am.
Okay. Here you can see this is a tertiary butyl ethyl substituted ketone, and upon treating with LDA, here no alpha hydrogen is there, and here two alpha hydrogens are there. So enolate will be formed uh, in this side. So it can either form cis enolate.
Ma'am,
Excuse me. Hmm.
ma'am, what is LDA here?
LDA is lithium diisopropylamine. I will draw its structure. It is a base. I will draw the structure. It is an amine, diisopropylamine N minus Li plus. So it is a base and it can abstract proton. So here alpha hydrogens are there. See here two alpha hydrogens will be there in this um, ketone, and this LDA, here this amine is having negative charge, it will abstract this proton. This LDA is a base, it will abstract this proton and it will generate an enolate. So here cis enolate will be formed. Why cis enolate is formed? Because um, here we can see this is cis enolate as this groups having higher priority, that is O lithium and this methyl group are coming on the same side. So it is cis enolate. And why cis enolate is formed? Because here the methyl group and the larger tertiary butyl group are coming in opposite side, so that they are not coming into contact. So that is the reason why here we are getting exclusively cis enolate, because the larger tertiary butyl group is coming opposite to that of the methyl group. They are not coming in contact. If they are coming in contact, there will be steric hindrance, so it will be unstable. So this stable cis enolate will be formed in this case. And we have seen that in diastereoselectivity, a cis enolate will give a syn aldol product. So this is the cis enolate. So once this oxygen will come downside, this double bond will go and attack on this aldehyde, and it will result in the formation of this syn aldol product. Is this clear?
Yes, ma'am.
Yes, ma'am. Okay. Now, here we are having a cyclic ketone, that is this cyclopentanone. Here also we are treating it with LDA. LDA is a base. So similarly, here also we have alpha hydrogens. So it will abstract one of the alpha hydrogen, and it will result in the formation of this enolate. This is a trans enolate. Why? Here the higher priority O lithium group and this group are coming opposite to each other. They are trans to each other. So this is a trans enolate. And since it is derived from cyclic ketone, it will give only trans enolate. So this trans enolate, when it is treated with this aldehyde, this will fall down, and this double bond will go and attack on this electrophilic carbon center, and it will result in the formation of this anti-aldol product. Clear?
Yes, ma'am.
Okay, so we have seen that here we are getting syn-aldol product in this case and anti-aldol product in this case. So this was our question. They are asking what is the major product P we are getting in this case, and what is the major product Q we are getting in this case. So our answer will be P is a syn-aldol product and Q is an anti-aldol product. Is this clear?
Yes, ma'am.
Now we can move to question 2. Coming to question number 2. The major product X formed in the following reaction is. Here they have a substituted cyclohexanone, and they are treating with 1 equivalent of LDA in THF at minus 78 degrees Celsius. So it will form one enolate. And after that they are doing alpha alkylation reaction using this alkyl halide, and they will get a major product X. They are asking us to identify what is this major product X. So how to approach this question? So here we know this is the cyclohexanone we are having. So LDA we know according to its structure it is very bulky base. See, it is having two isopropyl groups, and so it is a bulky base. LDA is a bulky base, and it will abstract a proton from this side. There is two possibility. It can abstract proton from this side, or it can abstract proton from this side. So since it is a bulky base, to avoid sterics, it will abstract proton from this side, and it will lead to formation of this kinetic enolate. Kinetic enolate will be less stable enolate because of less substitution. So because of this bulky base, it will lead to formation of this kinetic enolate, and once the this enolate is falling down, this double bond will go and attack at this double bond. Then this electron density will be shifting in this direction and this halide will eliminate. So we will get this product. Is this clear how it is happening? Since LDA is a bulky base, even though there is possibility for abstraction of proton from this side as well, because of this hindrance from methyl group, as a methyl group is present here and we are using a bulky base like LDA, the proton will be abstracted from this side and we will get this enolate. This enolate is called a kinetic enolate. So kinetic enolate will be formed. Then the electron density from this oxygen will fall down. Then this double bond will go and attack on at this center. Here the electron density will shift in this direction and this bromide will be eliminated. So we will get this product. Is this clear?
Yes, ma'am.
Okay, 1 second. Now, so out of these four, the correct option we got according to our mechanism is this option B. The correct answer will be option B. Question 2 is clear for everyone, right?
Yes, ma'am.
Okay.
Yes,
Now,
ma'am.
now we will move to question number 3. In a mixed aldol condensation with acetaldehyde and one other, here not aldehyde, it is a ketone, which one from the following is expected to give maximum yield of cross condensation product? So they are doing a mixed aldol condensation reaction. Two carbonyl groups is participating. One is acetaldehyde and one among these four ketones. So, out of these four ketones, which is expected to give maximum yield of cross condensation product? They are asking which will give the maximum yield of cross condensation product. In case of acetaldehyde and all these cases, there is possibility for self condensation as well. But they are asking which will give the maximum yield of cross condensation product. So, for successful cross aldol
Acetone, ma'am.
acetone will not, because acetone is having enolizable proton. Acetaldehyde is also having enolizable proton. So we can see for successful cross condensation reaction to take place, what are the factors we should keep in mind? See, for the kind of cross aldol reaction to work well, we must have two conditions. Two conditions we should keep in mind. One partner only must be capable of enolization. Capable of enolization means the presence of one alpha hydrogen is essential for enolization. So only one partner should be having that enolizable hydrogen, that is the alpha hydrogen. Alpha hydrogen is the hydrogen that is present adjacent to the carbonyl. So only one partner must be capable of enolization. But in our option, all the ketones that are given are having alpha hydrogen. In case of acetone, uh, this cyclopentanone, cyclopropanone, and cyclohexanone. In all these cases, they are having alpha hydrogen. Even acetaldehyde is having alpha hydrogen. Excuse me, I think someone want to join. So in all the cases, they are having alpha hydrogen. And even acetaldehyde is having alpha hydrogen. We can see the structure of acetaldehyde. Acetaldehyde will be CH3, C double bond O, H. So alpha hydrogen means the proton or the hydrogen that is present on the adjacent carbon to a carbonyl. So these three are called alpha hydrogen. In case of acetaldehyde, three alpha hydrogens are there. And in all these cases, see here in case of acetone also, six alpha hydrogens are there. In case of cyclopentanone, in case of cyclopropanone, cyclohexanone, all there are four alpha hydrogen each. And the second point, here the second point is the most important one. The other partner must be incapable of enolization and be more electrophilic than the enolizable partner. So here we are having an alpha hydrogen and it will be electrophilic. But out of these four, here this cyclopropanone will be more reactive and it will be more electrophilic sender. This carbonyl will be more electrophilic sender compared to these other three cases. Because of the ring strain of this cyclopropanone, it will be more reactive. So this can react with acetaldehyde and it will give maximum yield of cross condensation product. So the correct answer in this question will be cyclopropanone, as this is highly strained ring and this carbonyl will be highly reactive. It can react with acetaldehyde and it will give the cross condensation product. This sender will be more electrophilic. See, this second option we should take into consideration. This other partner should be more electrophilic. Here acetaldehyde is also having enolizable hydrogen. But here the cyclopropanone, this sender will be more electrophilic because of the ring strain that is present in this system. Is this clear? In all the other cases, in all the other cases, there are enolizable hydrogens present, but compared to acetaldehyde, here this sender will be more reactive because of the ring strain that is present in the cyclopropanone system. That is the reason why it will give the maximum yield of cross condensation product when it will react with acetaldehyde. Clear, right?
Clear, ma'am.
Okay. Yes, ma'am. Now we will move to question number 4. Here they are asking which of the following is the structure of most stable enol form of 2-methyl pendant 3-on, and they have given 4 options. These are the 4 options they have given and they have asked for the most stable enol form. So we need to know the structure of 2-methyl pendant 3-on before approaching this question. So this is the structure of 2-methyl pendant 3-on. Excuse me. So this is the structure of 2-methyl pendant 3-on. 1, 2, 3, 4, 5. So this 2-methyl pendant 3-on. So this is the structure of 2-methyl pendant 3-on. Now we need to see what is the most stable enolate that will be formed from this. We know that here there is one enolizable hydrogen and here there are two enolizable hydrogen. We should see if alpha hydrogen is present for that to be enolizable. So here we can see there is one enolizable hydrogen near this isopropyl group and here there are two enolizable hydrogen. So if proton is abstracted like this, alpha proton is abstracted by a base, it will result in formation of this enolate. And if this one of these two alpha hydrogen is abstracted, it will result in the formation of this enolate and this enolate. So here out of these three, this we can rule out. This is not possible. So out of these three, this 1, 2 and 3, here this will be having steric interaction with this isopropyl group. So this can be ruled out. We have seen that it will lead to formation of cis enolate in previous question because of the sterics. So here there will be steric interaction between this methyl and this isopropyl group. So this option can be ruled out. And out of these two, here this will be the most stable enol form. Why? Because it is most substituted. This is tetra-substituted enol form and this is tri-substituted enol. Tetra-substituted enol will be more stable than tri-substituted enol. So this will be the right option and it is the most stable enol form. Is this clear? Excuse me. So we have seen that this will be the most stable enol form that will be formed from 2-methyl pendant 3-on. And we have seen the reason why these two options are ruled out. Excuse me. Is it clear why this is the most stable enol form? This is the most stable enol form. And the reason is clear, right? Here, this is tetra-substituted enol and this is tri-substituted enol. So, tetra-substituted enol will be more stable compared to tri-substituted enol. And in this case, here the isopropyl group and methyl group are coming on the same side of this enol, and because of that, due to steric reasons, this will also be not stable. So the stable enol form will be first one, option A. Clear, right?
Clear, ma'am.
Okay.
Clear, ma'am.
Now we will move to question number 5. It is also a similar kind of question. Which enolate derived from 1-phenylbutane-2-on is the most stable? So these all four options are possible enolates that will be formed from 1-phenylbutane-2-on. This is the structure of 1-phenylbutane-2-on. These four options are possible options for enolates, and they are asking what is the most stable enolate. Here we can see if these two protons are abstracted, one among these two protons are abstracted, it will lead to formation of this enolate and this enolate. One among these two enolate will be formed. So here this enolate is in conjugation with the phenyl ring, and because of that it will be stabler. But here this phenyl group and this ethyl group are coming on the same side. Because of steric reasons, this enolate will not be stabler as we are thinking. So this can be ruled out. This is not the most stable. So this we will keep there and we will see the other two options. Here two more enolizable hydrogens are there in this carbon, that is adjacent to the carbonyls, and when this proton is abstracted by the base, it will lead to formation of this enolate or this enolate. Excuse me. So we have seen that from this 1-phenylbutane-2-on, when the proton is subtracted from this carbon, it will lead to formation of these two enolates. And when proton is subtracted from this carbon, it will lead to formation of these two enolates. And out of these four, because of steric reasons, here this benzyl group and this methyl groups are coming on the same side, and because of steric reasons this is not the most stable one. Here also same, here the phenyl group and the serial group are coming on the same side, and because of steric constraints it is not the most stable one. Then we have these two options. Here this is in conjugate compared to this one. Here this is in conjugation with this benzene, so this will be resonance stabilized, and because of that this will be the most stable enolate. Out of these four, this will be the most stable enolate. Clear, right? One second. You have any doubt why other options are ruled out? This is the most stable enolate, as this group is opposite to this ethyl group, and as also this alkene is in conjugation with this benzene, and because of that this will be the most stable enolate that will be formed from 1-phenyl butane 2 on. If anyone have any doubts, please feel free to ask. Can I move to question 6?
Yes, ma'am.
Okay. So this is question 6. Iodoform reaction is a confirmatory test for compounds having here COCH3, CH3, CONH2 and COOH. So before giving answer to this question, we should know what is iodoform reaction. So this is called iodoform reaction. Excuse me. Here this is the iodoform reaction. Here in presence of I2 and NaOH, here there is, sorry, here there is I2 and NaOH. In presence of NaOH, this is alpha hydrogen. Here there is 3 alpha hydrogen. So first one of the alpha hydrogen will be abstracted by this NaOH, which is a base. It will form enolate. It will result in formation of an enolate like R O minus double bond. And once it is falling back, this double bond will go and attack on I2, and it will result in formation of R double bond O CH2I. Okay, excuse me. Someone want to join. So here, first enolate will form like this R O minus double bond, and once this enolate is falling back, it will go and attack on this I2, and it will result in this formation of mono substituted product. Now two more alpha hydrogens are there. So in similar fashion, enolate will form and it will attack on I2, and if it is taking place multiple times, we will get this product in similar fashion. Now NaOH is there. This OH can go and attack on this carbonyl. It will lead to formation of a tetrahedral intermediate. And once that tetrahedral, excuse me, So this NaOH minus will go and attack on this carbonyl. It will lead to formation of a tetrahedral intermediate like R O minus this trisubstituted methane, triiodosubstituted methane, and OH. So once this enolate is falling back, this Ci3 minus group will be eliminated. Sorry for my dirty drawings. So once this enolate is falling back, this Ci3 group will get eliminated and we will get this carboxylic acid and CHI3, which is iodoform. This iodoform is giving yellow coloration, and this can be used as a test for detecting methyl ketones in the system. So this reaction is called the iodoform reaction because iodoform is getting released in this reaction and it is giving yellow coloration. This iodoform is having yellow color. Excuse me. Iodoform will be having yellow color, and so this reaction can be used for detecting methyl ketones in the system. This is called iodoform because here we know, see, if it is CHCl3, it is called a chloroform. So this iodoform is an old name for iodomethane. And in this reaction, nucleophilic substitution at the carbonyl group, it is resulting in formation of a carbon-carbon single bond cleavage. So here the correct answer will be COCH3. Methyl ketone is necessary for iodoform reaction to take place. So this iodoform reaction can be used as confirmatory test for compounds having this methyl ketones. Is this clear?
Yes, ma'am.
Okay. I think someone want to join. So now coming to question number 7. Here they are asking what is the final product of given reaction occurring via the silyl enol ether intermediate. Here there is a disubstituted ketone, and treating with triethylamine and TMS chloride, it is resulting in the formation of the silyl enol ether. So once silyl enol ether is formed and it is treated with TiCl4, titanium tetrachloride, and this benzaldehyde, what is the major product that is formed? That is our question. We need to find out the final product that is forming in this reaction. So they have given four options. We need to identify which is the correct product that is formed in this reaction. This is an aldol reaction. Okay. One second. Everyone, please try to join by 6 o'clock. So, this is an aldol reaction. So, we have to identify what is the product that what is the final product that is formed in this reaction, and four options are given here. Out of this, only one will be the right answer. We have to identify which is the right answer. So coming to mechanism, here this is a general mechanism. We are having a silyl enol ether, and when it is treated with benzaldehyde and titanium tetrachloride, first a silyl ether of aldol will be formed in this fashion. We will see the mechanism. So first a intermediate, a silyl ether of aldol will be formed, and when we are doing workup with water, it will result in formation of aldol product. So coming to mechanism, we are having a silyl enol ether, And in presence of this titanium tetrachloride, this titanium tetrachloride is a Lewis acid. It will coordinate with this benzaldehyde, and it will make the benzaldehyde more electrophilic by coordination. It will coordinate with this benzaldehyde in this fashion, and it will make the benzaldehyde more electrophilic. Now the lone pair of electrons from the silyl enol ether will come in this direction. This double bond will go and attack at this electrophilic center, and this positive charge on the oxygen will be neutralized. This is the aldol addition step. Okay, so we will get this intermediate. Now the chlorine atom, we were having titanium tetrachloride, one chlorine atom will be removed, and that chlorine atom will come and abstract this silyl group, and this oxygen group will be, this positive charge on the oxygen will be neutralized. We will get this product. This trimethyl silyl group is removed by chlorine ion, so we will get this product. Then what will happen, there is an enol group here. This uh, this group will go and attack on the silyl chloride, trimethyl silyl chloride, and TiCl4 will be removed, and this trimethyl silyl group is recaptured at this position, and we will get this intermediate what we have seen here. Okay, so what is necessary is that a Lewis acid is needed. Here titanium tetrachloride we are using to get silyl enol ethers to react. These silyl enol ethers are very stable enol ethers, and because of that a Lewis acid is needed to get those silyl enol ethers to react. And the key step is an aldol attack of the silyl enol ether with the Lewis acid complex electrophile. This is the key step in this reaction. A silyl enol ether is there, and this electrophile should be coordinated with a Lewis acid. Here titanium tetrachloride is the Lewis acid. So this aldol addition step is the key step in this reaction. Then this chloride ion will come and abstract this trimethyl silane, and here the positive charge on this oxygen will be neutralized. Then once the chlorine will come and take this titanium trichloride, this group will go and attack on this trimethyl silyl chloride, and we will get a silyl ether of aldol in this reaction. And when we are doing workup, we will get this aldol product. This is a general mechanism. So is this clear for everyone what is happening here?
Yes, ma'am. Clear, ma'am.
Okay.
Yes, ma'am.
So in our question, we are also having a silyl enol ether, and we are given titanium tetrachloride and benzaldehyde. We need to identify the product. So what will happen here? Here this lone pair of electrons on this oxygen will fall down, and this double bond will go and attack on this benzaldehyde, which will be coordinated with this titanium tetrachloride, and we will get, what will be the product that will be formed. This is the product. Here see, CH3 is there, double bond O, CH3 will be there, and this will form an alcohol, and a phenyl group will be there. So this is the product that will be formed. Since the previous mechanism is clear, you can try working out this reaction, and you will get this as the major product. Clear?
Yes, ma'am.
Okay. I think someone need to join. Now coming back to the question. So here we are getting the silyl enol ether will react with this benzaldehyde, and we will get this aldol product. And we have seen how the mechanism is taking place in general. Now we will move to question number 8. So this is the question. Identify the major product of the given cross-aldol reaction. So they have given diethyl malonate, and they are treating it with this isopropyl aldehyde in presence of this R2NH, which is a base, and acetic acid. So they are asking to identify what is the major product formed in this cross aldol reaction. and 4 options are given. So we will see what is happening in this reaction, what is the mechanism for this cross aldol condensation reaction. Before going into that, one second. So this is the mechanism. We are having diethyl malonate and R2NH is the base. So this R2NH can abstract this proton. So this proton will be more acidic as it will form a stable conjugate base. So this proton will be abstracted. It can result in the formation of this enolate, or here this can form this enol form, and from there this proton can be abstracted and it will result in formation of this enolate. This is the enolate that will be formed from diethyl malonate because this is more acidic proton as it is stabilized by these two carbonyl groups. If the conjugate base is stable, that proton's pK value will be low and it will be more acidic. So here this is the enolate that will be formed, and we are having this aldehyde which is electrophilic. So once this enolate is falling down, this negative charge on the oxygen is falling down, this double bond will go and attack on this electrophilic aldehyde center, and O minus will be formed like this, and it will abstract proton from this acetic acid, and an intermediate like this is the aldol product that will be formed. Now we are having this aldol product, and we are having one more enolizable proton on this diethyl malonate. So again this base will abstract this proton, again an enolate will be forming, and once the enolate is falling back, this hydroxyl group will be eliminated and we will get an alpha beta unsaturated compound. So this is the major product that is formed in this reaction. So once we are having this diethyl malonate and this aldehyde, in presence of this base and acetic acid, it will result in the formation of this alpha beta unsaturated compound. Is the mechanism clear for everyone?
Once again, repeat, ma'am.
Okay. Here, this is the here out of these two, here this will be having more acidic proton. So this R2NH is a weak base, so it can abstract this proton from this most acidic proton, and it will result in the formation of this enolate. It will abstract this proton, this double bond will be formed and this carbon oxygen bond will be broken, so it will form this enolate. So this enolate can attack on this electrophilic center of this aldehyde. So once this negative charge on the oxygen falls down, this carbon double bond will go and attack on this electrophilic center of this aldehyde, and it will lead to formation of this species. So this is the aldol species. This O minus can abstract proton from acetic acid, and it will result in the formation of this aldol product. Now we know that here one more proton is there, and also we are having this base in the system. So this base will abstract this proton. Again enolate will be formed, and once the enolate is falling back, this OH minus will be eliminated and an alpha beta unsaturated compound will be formed. So this is the whole mechanism taking place, and this is the reaction. Is this clear? What is happening?
Yes, ma'am.
Okay. So, in this question, they are asked to identify the major product of this cross aldol condensation reaction. And the major product, according to the mechanism we have seen, is this one, alpha beta unsaturated compound. So, the correct answer is this alpha beta unsaturated compound. One second, I think again someone need to join. So, now coming to question number 9. Here they have asked to predict the structure of the enolate that will be formed in the given reaction. They have given one ester and they are treating it with LD at minus 78 degrees Celsius, and they are asking to identify what is the structure of enolate that will be forming. So we are having here, as we can see, this is the structure. C double bond O E T. So this is the carbonyl group, and the proton that is present adjacent to the carbonyl will be in this side alone. So this is the alpha hydrogen, and it can be abstracted by this base like LDA. Excuse me. Sorry. So this is the alpha hydrogen, and that alpha hydrogen can be abstracted by the base like LDA, and we will get, this is the structure of LDA. It is a base. Here the negative charge on this nitrogen can abstract this alpha hydrogen. Then the electron density will be pushed in this direction, and this carbon oxygen bond will break, and we will get this enolate. And diisopropyl amine will be generated. So this is the structure of the enolate that will be formed in this reaction. So out of these four options, this one is the right option as we have seen in this mechanism. So is it clear? The correct answer is this one. It is clear, right? How the enolate is generating.
Yes, ma'am.
Okay.
Yeah, ma'am.
Now we will move to question number 10. So here they are asking identify the major product from the following reaction. Here they have a ketoaldehyde system and they are treating with KOH ethanol, and a major product P will be formed. There is possibility for formation of many products as there are many enolizable hydrogens, but they are asking what will be the major product that is formed in this reaction. So we know that here there will be enolizable hydrogen on this carbon, on this carbon, and on this carbon as it is adjacent to carbonyls. So here, which will be the hydrogen that upon enolizing will give the enolate, and then it will attack on the electrophile to give the product P. We can see the mechanism. Here we can see in presence of KOH, if this hydrogen is abstracted, the hydrogen on this carbon is abstracted, the hydrogen on this carbon is abstracted, it will result in the formation of this enolate. Okay, here there is two possibilities, but here we can see when this hydrogen is abstracted, it will lead to formation of less substituted enolate. Here this is tri-substituted enolate. When hydrogen is subtracted from this ender, it will result in formation of di-substituted enolate. So this enol will be formed. Now once this negative charge on this oxygen is falling back, this carbon-carbon double bond will go and attack on this electrophilic center of the aldehyde. Here aldehyde is having more electrophilicity. So this carbon-carbon double bond will go and attack on this aldehyde, and we will get this intermediate. This is the aldol intermediate, and once again enolate can form. Here hydrogen will be there. Enolate can form, and once it is falling back, this double bond will form, and the hydroxyl group which will be formed here, it will be eliminated, and we will get this product. One second. And there is another possibility for formation of enolate on this carbon. If enolate is forming on this carbon like this, once it is falling, it will go and attack on this ketone. But compared to aldehyde, ketone is less electrophilic. Aldehyde is more electrophilic than ketone. So, this formation of this product from this aldehyde derived enol will be less feasible compared to this product, which is derived from this. Everyone, please mute. So the formation of this product will be less feasible as the electrophilicity at this carbonyl of this ketone is less compared to when enolate is attacking on this aldehyde in this case. So now understand why this will be formed majorly compared to this one. Here, enolate is going and attacking on aldehyde, which is more electrophilic. So this is feasible because enolate is nucleophilic. It will go and attack on this electrophilic center of the aldehyde, and electrophilicity of aldehyde is more compared to ketone. So here the attack of this enolate on this ketone will be less feasible. This reaction rate will be low, and because of that, this formation of this product will be less feasible compared to this one. So in our question they have asked which is the major product that will be formed, and we have seen that this one will be the major product that will be formed and not this one. Okay. Anyone have any doubt regarding the mechanism of this reaction?
No, ma'am.
Okay. Now we will move to question number 11. Here phenol on reaction with formaldehyde and dimethylamine mainly gives. So phenol upon reaction with formaldehyde and dimethylamine, what will be the major product that is formed, and they have given four options. So we will see what is the mechanism or what is the reaction that is taking place here. So formaldehyde and dimethylamine, it upon reaction. Here this dimethylamine, it will undergo nucleophilic attack on this electrophilic center of formaldehyde. So it will result in the formation of this species, and then proton transfer will take place from this nitrogen to oxygen, and it will result in formation of this species. Then, in presence of HCl, this OH will be protonated, and when the lone pair of electrons from nitrogen is falling in this direction, water molecule will be eliminated, and we will get this imine salt. Okay. So now we are having phenol, and when the lone pair of oxygen on this phenol is falling down, this double bond will go and attack on this carbon, and this positive charge on nitrogen will be neutralized. We will get a species like this. But here the aromaticity of the system is lost. So now since aromaticity should be regained, this will undergo tautomerism, and this keto form will be converted into this enol form, giving back this aromatic system. So we will get this as the major product in this reaction. Clear? Is this clear?
Yes, ma'am.
Okay. So out of these four options, our right answer will be option A. Formaldehyde and dimethylamine will react to form iminium salt, and phenol will attack on that iminium salt and undergo tautomerism to give this product. I hope the mechanism is clear. Now we will move to the last question of this assignment, which is question number 12. And this question is like a repeated form. We have already seen iodoform reaction. So here they are asking identify the starting material of the following iodoform reaction. X upon undergoing iodoform reaction is giving this iodoform and this carboxylate. So what is the right answer? Anyone can answer. Option A, B, C or D. We have discussed iodoform reaction in one of the previous question. So you can,
B.
yeah, B is the answer.
B.
Yeah, B is the correct answer. Because iodoform reaction is used to identify methyl ketones in the system. So in this case, there is a methyl ketone present. So the right answer will be option B. I hope this is clear for everyone. If you have any doubt regarding any of the question, feel free to ask. This is the last question in this tutorial. If anyone is having no doubts, we can wind up this session. Thank you for attending my class. Like everyone, please try to join before by 6 o'clock so that we will not get any disturbance or interference in between. So I will be. Hello.
Ma'am, where can we find this recorded video?
You can
This
find in YouTube. YouTube
YouTube.
link I
Okay,
think they
thank
will
you.
provide to you.
Okay, ma'am. Thank you.
Okay.
And what's the YouTube channel name?
PMRFTA Anisha Suresh. I will share you the link. Like, 1 second. This is the YouTube channel. Sorry. PMRF NPTL TA Anisha Suresh. And here I have added the previous 4 tutorials as well. You can feel free to see. And if you are having any doubt, you can ask. PMRF NPTL TA Anisha Suresh. That is the channel name. Okay, if no one is having any doubts, we can wind up this session. Thank you for attending this session. We will meet again next Tuesday from 6 to 7 p.m.
Okay, ma'am. Thank you, ma'am.
Thank you. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank
Thank
you.
you, ma'am.